Today's topic, second order RLC system step response. And we know, so we have seen RL and RC system step response. For RL system step response, we found that the current was increasing in the circuit and voltage was decreasing across inductor. For RC system, we found that the voltage across capacitor was increasing and it was reaching the input. So input generally we give unit step. So at the end, when T is very high, the capacitor across capacitor, the voltage also will reach to 1 volt. Sometimes it might not reach to 1 volt. So in that case of defective capacitor, so those cases we have not done so far. Those cases means when we study steady state response, then only all those cases we will see that we have given 1 volt input, capacitor voltage, RC circuit, ideally it should be 1 volt across capacitor, but sometimes it might not be 1 volt. Okay, so in that case, suppose output is zero point 0.8 volt. So in that case, what we say is 1 volt is the input, zero point 0.8 volt is the steady state output. Steady state output, not a transient. Okay, so in that case, 1 minus zero point 0.8, so that is zero point 0.2 volt will be the steady state error. So how to find out steady state error for any system? That study also we will do. But today, first we will do for RLC second order system. So I don't think Mr. Pranav will join. So before we go any further, please turn on your video and let me take the snapshot. Yes, it is taken. Thank you. You can turn it off. So I really thank you for being with me for last 19-20 lectures. So it is very good that you are attending every day. Thank you for that. Okay, so let us now go for the topic. So this topic actually was told to you, the performance specification. So now a very brief of about why the second order RLC, step response or transient response, which is the same thing. So impulse response is called as natural response, and the step response is called as a transient response. And not only the transient part, we are getting both the parts, transient at the starting and steady state for T very high. And then also step response is called as transient response. So what will be the input? Input to the circuit will be unit step. Circuit is second order RLC. And there will come two very important things. So for first order system, we found out there is only one design parameter. So if it is LR circuit, it is L by R. Unit is second, which is called as time constant. अभी तक मैं तुम लोगों को time constant का definition नहीं बताया. So what I will do is after the IA, I will conduct one lab session, very small lab session extra for half an hour or so. I will show you by MATLAB exactly how to define the time constant. So I could show it now, but before IA, let it be. Someday in the evening, I will show you how to find time constant and how to go for it. So by MATLAB, all the graphs and also code also I have posted. That code also you can check with the notes of 18th lecture. So time constant definition we will do. So if it is first order system, there is only one design parameter which is called as time constant. It is tau. How to calculate the value you know, but in graph you have not seen what is time constant. So that part I will show you by a MATLAB session extra. For second order system, you can write down there are two design parameters. First design parameter is called as omega n. I think you have heard about it. So for RLC circuit, you have studied resonance frequency. What is resonance frequency? Resonance frequency is 1 by 2 pi root LC. That is the resonance frequency in hertz. Okay, the same thing as omega n, but omega n is not given in hertz. Omega n is given, omega n is the natural frequency or resonance frequency you can call. Omega n is given by 1 by root LC, because omega unit is not hertz, omega unit is radian per second. Okay, so whenever we are trying to find hertz from omega, what I do is we divide omega by 2 pi. Okay, so a relation between omega and f is omega is equal to 2 into pi into f, and pi is 3.14, pi is not 180. So whatever pi we are talking about here, it will be in radians. So pi is 3.14, 2 into 3.14 into f. Okay, so if I tell you that it's a 10 hertz frequency, how much it is in radian per second? So it is 2 into 3.14 into 10. That means 20 into 3.14. That means 62.8 radian per second. So that is the way we calculate or convert hertz into radian. Now, why this thing we are supposed to study? Because first we have to study two things. One thing is called as natural frequency. You have idea about natural frequency, that if you just leave the circuit and if there is no response, so the circuit will oscillate at a resonance frequency, that is omega n. Okay, and it depends on RLC component. Not, it doesn't depend on R, it depends on LC. So omega n is equal to 1 by root LC. ये formula लिख कर रख सकते हो, omega n is equal to 1 by root LC. All this I will show you, it is given in my notes. Second parameter which you don't know about it now, it is called as damping. Okay, zeta. Okay, so zeta is actually against the gain. So more is the damping, less will be the gain. And we know the inverse relationship between gain and stability. So more is the gain, less is the stability, less is the gain, more is the stability. And zeta के साथ stability का क्या relation है? More is the value of zeta, more is the stability. So ये तीन चीज तुमको एकदम clearly तुम्हारे दिमाग में रहना चाहिए. First thing is, if gain is more, stability is less. Correct. Second thing, if zeta is more, damping is more, stability is more. Okay, so relationship between damping and stability is directly proportional. Relationship between gain and stability is inverse. Okay, so ये एक line लिख के रखो, that zeta is directly proportional to stability. More is the stability, more is the zeta, or otherwise we can say vice versa. And third thing is zeta and gain. Okay, so more is the value of zeta, less is the value of gain. So zeta and gain inversely proportional, gain and stability inversely proportional, zeta and stability directly proportional. तो पूरा control system ये तीन चीज का खेल है. First one is zeta damping, second one is gain, third thing is stability. So zeta and gain inversely proportional, gain and stability inversely proportional, zeta and stability directly proportional. So we will see what are the effects of zeta, okay, and what is the effect of omega n if the component values changes. So I change the value of R, L and C. Circuit sometime will become overdamped, underdamped, undamped, critically damped. So there are four cases in second order RLC response. All these things we are going to see today. So just see what are the performance specification. The study of control system. I'm just reading the slide. The study of control system essentially involves the evaluation of transient and steady state response. ये दो definition prepare करना, लिख के रखो. What is meant by transient response? So the definition of transient response is as soon as we connect the circuit to some external input. Okay, so as soon as some external supply voltage or some energy input or some input is given to the circuit, whenever the energy is given to the circuit and the circuit behavior, they actually fight with each other. It's like the vaccine. Okay, as soon as the vaccine is given to the body, we know that in due time the fever will reduce. Okay, as soon as we give the vaccine, there is a fever, there is a body ache. Okay, and there may be hand is swollen, hand may be pain. Okay, so that is actually the transient response of the vaccine. What is the steady state response? All this thing dies down and you are very comfortable. You will not be having corona. That is the steady state response. But initially, whenever we give the vaccine, that is the external agent, we get some kind of uneasiness. Okay, possible. And किसी किसी को होता नहीं है. Okay, nothing happened. So I took Covishield. I'm not proud, but nothing happened to me. Maybe in second dose of Covishield, I'll be getting fever or something. Okay, so nothing happened to somebody. So for not every system will be having a huge transient. Okay, some system is having small transient behavior. That means small deviations from its standard output at the initial stage. But ultimately, all the transients die down and they streamline and system gives steady state response. So whenever we give this kind of response, that is a step input to the RC circuit, we found initially the graph was starting from 0, it was increasing and then it got steady and final value was exactly same as the input. So if input was 1 volt, final output was 1 volt. But initially it did not happen very fast. Initially it was a building up process, then it became 1 volt. So that part, when the input is increasing or changing, in output, sorry, output is changing, that part is called as transient response. Response means output. What is meant by steady state? After a long time, when the output has become stable, that is called a steady state response. So this is the definition of transient. So the definition is, as soon as we are inputting some energy to the system, the energy, it reacts or interacts with the system components, and at that time we can see that the output is not stable. Output is oscillating or maybe undulation or some kind of things are happening. It is not steady. It is not steady at a certain value. That part of the response at the initial part is called as transient response. What is called a steady state response? So a transient response happens generally at t is equal to 0 or t very small value, just after we have connected the input. Steady state response happens when t is very high. So you have connected the input, and maybe after 5 hours you are checking how much is the output. Output has become steady. So when t is very high or t is equal to infinity, very high value, at that time whatever is the response of the system, that is called as steady state response. That means the output has become steadied. Okay. Like we watch one day cricket. Okay. So in that case, first 5-10 overs is like a transient. Okay. Test cricket, first 1 hour, they say, पहला 1 घंटे में wicket गिरा तो ठीक है. Otherwise, this batsman will keep on playing forever. So because in the first 1 hour, it's a new condition. Okay. And in that case, the wicket behaves differently. So as time goes by, system leaves the transient response and it enters into the steady state response. So we are going to study that for a second order RLC system. So we are going to see the transient response, steady state response, robustness of the performance against model uncertainties and disturbances. So system model can be there, and that might not be totally known to us. Okay, suppose I'm giving some kind of input, 1 volt, 2 volt input to the circuit, and it is behaving properly. Suddenly I increase the input to 10 volt and circuit might burn. Okay, so robustness means any kind of input you are giving, any kind of response you are asking from the system, whether the system is able to sustain that, whether the system is able to sustain any kind of shock. Okay, so that we have to check for different kinds of inputs. So robustness, robust is word ka actual meaning in control system is multi input multi output. Example, car. So robust system is a car. Okay, there are many inputs. You are giving input through brake, you are giving input through maybe accelerator. There may be AC on, AC off, light on, light off, headlight off, windscreen on, windscreen off. So all these are inputs to the system. Okay, so for many robust system, we have to check whether the system is behaving perfectly under some kind of uncertainties and disturbance. So car is running up to 100 kg if you're sorry 100 kilometer per second. If you are pressing the accelerator, car is working fine. As soon as you cross 100 kilometer, the car starts vibrating. Okay, so that's why they are saying under all kind of uncertainties and all kind of disturbances. So shuru mein the car does not show any vibration because your speed is low. Suddenly you are increasing the speed beyond 100 kilometer and the car starts vibrating. So that is the unknown condition for us. So what is the ultimate decision? That we should not drive this car because it has become old. Okay, beyond 100 kilometer per hour speed. The nature of the transient response of a linear control system is revealed by any of the standards signals like impulse, step, ramp, parabola, as its nature is dependent upon system poles only on the type of this input. So we have not studied so far what is the pole position and what is the response of the system. तो एक अच्छा स्टडी है, हम देखेंगे. We know what is pole. Okay, we know transfer function. So there is a numerator polynomial, there is a denominator polynomial. All the roots of the denominator polynomial is called as a pole. So there are different frequencies. Suppose denominator एक polynomial है, उसको factorize करो. What you find is s plus 3, s plus 7, s plus 9. That means there are three pole frequencies: 3 radian per second, 7 radian per second, and 9 radian per second. If you are giving all those frequencies, the circuit output will jump. Suddenly it will go to some kind of resonance. Okay, so there's it's a good study. So our step is generally, so here it is written, very important thing, poles and all this, it is therefore sufficient to analyze the transient response to one of the standard test signals. A step is generally used for this purpose. So generally for any system complete analysis, we give the step input to the system and we check that how the system is behaving to step input. Suppose a student comes to me and I want to guide him for his PhD. Okay, what I will do is I will prepare a question set beforehand, and I will ask him, "Chalo, you answer this, and let me see how much you can score in this question paper out of 10." Because those questions are parameter related to his research proficiency. Okay, so I find that he has scored only 2 out of 10. That means I understand that research wise his is very weak. Okay, so that is a standard questionnaire that I have prepared for the student to test his proficiency in research. Step input is like that. So step input is like the stethoscope of the doctor that they use. Okay, you just give the step input to a system, just check what is its response, and depending on that we can understand about the system. So for some systems step response is slow. That means we understand that the system is having more zeta. अभी बहुत इंपॉर्टेंट बात मैं कह रहा हूँ, ये सब नोट करते रहो. If zeta is more, system response, step response. So step response was 1 volt I have given to the system. Okay, so I'm taking generally the output of the RLC circuit across capacitor. So how the capacitor voltage rises when inductor, resistor, and capacitor, all these three things are there in series. So I find that the circuit capacitor voltage rises very slow. What is the understanding? Understanding is zeta for the RLC circuit. Okay, what is the formula of zeta? It is R by 2 divided by root under of C by L. Okay, so there are two parameters I told you, omega n 1 by root under of LC, and zeta. Zeta is R by 2, that is resistance by 2 into multiplied by root under of C divided by L. So all R, L, C, all these three components are coming in zeta. So zeta is more. Zeta is more means resistor value is more, or capacitor value is more, or inductor value is less, because it is R by 2 root under of C by L. So when R is more, C is more, L is less, in that case circuit zeta becomes more. If zeta becomes more, that means output does not increase fast. So zeta is kind of, not exactly, zeta is actually kind of the time constant. But difference is more is the time constant, system is slow. In this case, more is the zeta, system is slow. Okay. So that's why step response for a second order system is very important to know what is the fastness of the system. Okay, what is the rise time of the system, what is the peak time of the system, what is delay time of the system, all सब चीज दिखाएंगे. So a step is generally used for this purpose, just to know the transient response and steady state response of the system. So from the steady state point of view, the easiest input is generally step input. It requires only maintaining the output at a constant value and all those things. A more difficult problem is the tracking of a ramp input. So whenever we give the same ramp input to the system, we will find that system will freak out. Okay, so I will show you all the outputs. Okay, now next is I will show you the output, and next we will go to my notes and I will explain you how the output comes. So this is a very important question. So ये लिख के रखो 6.2.1 from the book of M Gopal. So that book is also given to you. So you can prepare this thing from that book of M Gopal, 6th chapter, topic 2.1. So that's why this is 6.2.1. This question is explain with the diagram. So this diagram you have to draw. What is the unit step response, a typical unit step response of a second order underdamped system? This word is very important, which is not written here. Underdamped. What is meant by undamped? तो ये भी लिखते रहो. Undamped means zeta is equal to 0. In that case, the system will only oscillate. Okay, only the output, system output will be sinusoidal. Though you are giving the step input, okay, I will show you it by practical lab session. I'm giving a step input to the system, but what I will find is if zeta is equal to 0, zeta is equal to 0 means R by 2 root under of C by L. So if I make R is equal to 0, in that case the zeta value will become 0. So RLC circuit in that case becomes LC circuit because R value is 0. Or we can say it's a RLC circuit with R value as 0. So if it's a RLC circuit with R value as 0 or zeta is equal to 0, for the step input, output will become oscillatory, sinusoidal. Okay, so that is called as undamped response. And that frequency is called as omega n, or natural frequency given by 1 by root LC. सेकेंड इज इफ यू आर इनपुटिंग आर, थोड़ा सा आर तुमने सर्किट में डाले, रेजिस्टेंस का वैल्यू थोड़ा बड़ा है ओके, सपोज दैट रेजिस्टेंस इज अ वेरिएबल रेजिस्टर, यू कैन slowly increase the resistor value. So previously the R value was 0, I was giving step input, unit step input, the output was oscillatory, sinusoidal. Now I have increased little bit resistance in the circuit. Now the response will become like this. So there is also oscillation, but this oscillation is not a sustained oscillation, because you can find here it is a reducing kind of oscillation. So this oscillation is called as a damped oscillation, DAMPED, damped oscillation, and that is actually called as a underdamped oscillation. Why there is a damping? Because whenever there was R was 0, there was no resistance in the circuit, system was behaving the way it wants, and omega n was its natural oscillating frequency. Now as I've input some resistance, that oscillation will reduce, and you will find that this frequency of oscillation, whatever is seen here in this diagram, it is little lesser than omega n. What is this oscillation called? This oscillation is called as damped oscillation, omega d. And what is the formula? Omega d is equal to omega n into root under of 1 minus zeta square. And in this case, zeta value is in between 0 and 1. That is very important. So zeta 0, undamped. Zeta between 0 and 1, it is called as underdamped. Is it understandable so far?
Yes, sir.
Yes, sir.
Okay. So zeta 0 is undamped. Zeta between zeta negative नहीं होता है. Okay, because zeta is r by 2 root under of c by l. All the values are circuit components. So all the values you plug in, and you will be finding that zeta is some positive value. It's a value of circuit resistance or circuit fastness. How fast the circuit will rise, or how fast the output will rise. That factor we try to figure out from the R, L, and C value. So R can be 0, zeta can be 0. In that case, it's an undamped oscillation, it will be only oscillation sinusoidal. R value little bit you increase, so zeta value will become little more in between 0 and 1. So C and L constant. So C is 1 farad and L is 1 Henry. Okay. In that case, R value suppose you have kept as 0.5. Okay. So C is 1, L is 1. So root under of C by L is 1. वो निकल गया. R value is suppose 1. How much is the damping coefficient zeta? Zeta is equal to 1 by 2, because that 2 is a formula. So in that case, zeta is equal to 0.5. R you have kept 1 ohm, C you have kept 1 farad, L you have kept 1 Henry. What is the value of zeta? 1 by 2 root under of 1 by 1. So that comes to be 0.5. In that 0.5, this kind of response you will be able to see. So this is not a sustained oscillation, this is a damped oscillation. Damped because the output is reducing, and initially you can see what is the starting point of the output. You can see now, what is this one? Can anybody tell me what is this one? This one is the input. This is one is the unit step input that I'm giving to the system. Okay, and input and output is shown in the same graph. ये देखो लिखा हुआ है ऊपर YT unit step input. So I have shown the input first, and then I'm finding that the output is rising. Okay, rising, and it has gone to peak. Okay, so this time is called as peak time, when the peak is there, and you are giving 1 volt input, but you are finding that output may have gone to 1.4. Amplifier circuit nahi hai ye, it's a simple RLC circuit. But in this case, a very typical phenomena, you are finding that output is crossing the input, though it is not amplifier circuit. This happens due to some kind of resonance. Okay, so output is reaching, so this time is called as peak time, and whatever is the percentage MP, suppose the input is 1 and this peak amplitude is 1.4, in that case this percentage MP we called as a 40%. Okay, because in this case this input is 1 but this peak is 1.4 amplitude. In that case I say that a percentage MP is, or percentage peak magnitude or peak overshoot, ये नीचे लिखा हुआ है देखो, peak overshoot MP. What is that? Y at TP. Y at TP means output at TP. What is the TP? TP is called as a peak time. Okay, though you are giving step input, but we are finding that response is oscillatory because R value you have kept as 1, C and L value you have kept as 1, and we are finding that zeta is equal to 0.5. So because of this underdamped condition, we are finding that response will shoot up, and it will shoot up to 40% of the input. So input is 1, and if the output shoots up above zero point 0.4, okay, that means 40% of the input. So this is how to calculate the percentage MP. Okay, so what is the input at t is equal to, sorry, what is the output at t is equal to 0? Can you just tell me? Output at t is equal to 0 is 0. Is it observable? This is the output step response. So this dark one is the step response, and this parallel line DC is the step input. And I told you Vinay was not there, so step input starts at 0 plus. So you have connected the switch at t is equal to 0, but there is a propagation delay for that wave to reach to the load and create a high 1 voltage. So at 0 plus 2, t is equal to infinity. T is equal to infinity is called as a steady state. So right side, this side, this is called as t is equal to infinity, and initial t is equal to 0, this is called as a initial response. So all this, whatever undulations and all these things you are seeing, it is called as a transient. Okay, so all this undulation, and you are finding this is a damped oscillation, and after that at this time you are finding that, so ts is given here. After ts you are finding that output has almost it has become stabilized. And what is the final value of the output? Final value of the output is 1. That also you have to understand. So more you are going towards the right side, t increasing, you are finding that this oscillation will die down, and the final value of the response will be 1 volt. Input is 1 volt, output is 1 volt. Input minus output is 0. So in that case steady state error will be 0. Okay, so what all times we are supposed to study? Time we are supposed to study is rise time. What is the rise time? For the first time when the response touches the input. Okay, so this response is actually crossing the input and going above. So for the first time when the output touches the input, this point is called as a rise time. Okay, there is another definition which is not shown here. It is called as a delay time. What is the delay time? So delay time will be half of this height. So wherever the output touches the 50%, so in my notes I will show you, wherever the output touches to zero point 0.5 amplitude, that time you have to project below, and you have to say that that is called as delay time given by TD. So four time specification is there and one amplitude specification is there. First time specification is TD. Okay, so this is the output response rising. TD is when the output reaches to the 50% of the input. So input is 1, 50% of the input is zero point 0.5. So time taken by the graph to reach to the 50% is called as TD or delay time. Next is TR. Okay, when the output reaches to the 100% for the first time. Again, you are finding that the waveform is dropping, and here also it is 1. Again, it is rising. Here also it is 1. वो सब नहीं देखना है. Okay, that is happening for the second time, third time when the output is 1. वो नहीं देखना है. For the first time, well, in the transient case for the first time, so why this is transient? Because output is increasing and then oscillating and then it is going towards steady state. So steady state is happening at TS. So you can find here TS. Is the TS visible to you? My arrow is there. Is the TS visible to you?
Yes, sir.
Yes, sir.
Okay, so before this, whatever is there before TS, left side, it is called as transient, and right side of the TS is called as steady state. So TS is something who is deciding what is the steady state and what is the transient. So left side of the TS is transient region of the waveform. I can ask you in the exam, I can give you some waveform and I can ask you, बोलो इसमें transient region कौन सा है और steady state region कौन सा है. So left side of the TS is transient, that means जब वो undulations हो रहा है, and right side of the TS is steady state. Now you can ask me, sir, right side of the TS, it is not entirely steady, it is still oscillating. Yes, but oscillation has come within the limit. So there are two limits. When the oscillation is less than 2% is called as 2% TS, and when the oscillation is less than 5%, 5% of its amplitude. What is meant by 5%? 1 का 5% कितना है? 0.05. Okay, so this is input is 1 ka 5% is 0.05. So when this waveform enters 0.95 to 1.05, what is 0.95? 5% less than the actual input. ऊपर वाला arrow और नीचे वाला arrow. So there are one region shown, amplitude region. This amplitude region is 0.95 to 1.05. That is 1 से 5% नीचे से लेके 1 से 5% ऊपर तक. So whenever the waveform enters this region and stays within this region, ये waveform right में जाके बढ़ता नहीं है, because it is damped oscillation. It is continuously reducing and it is getting steady. So finally at t is equal to infinity, amplitude will be 1 volt only. Okay, but in that process, when it is entering this region, 0.95 to 1.05, and it is staying within that, so that TS is called as 5% settling time. What is the formula for that? 4 divided by zeta into omega n. Okay, all those formulas I will show you because we have to do numerical with that. And when if this here it is shown as 0.02, that means it's called as 2% settling time. That means whenever this oscillation enters amplitude 0.98 up to 1.02, then that time is called as TS 2%, and that is more stable. So TS 5% means oscillation will be little more, 5%. That means amplitude will be in between 0.95 to 1.05. But again, you are going, time is increasing and the oscillation is dying down, and oscillation has become less. That means waveform has become more steady, and we are in the range of 0.98 to 1.02. In that case, it is called as a 2% settling time. So 5% settling time comes to the left side. So you can see here TP. TP के बाद आता है 5% settling time. What is the formula for that? 3 divided by zeta omega n. Then it is within the range of 1.05 to 0.95. Again, the oscillation keeps on reducing and it enters the region of 2% settling time, that is 0.98 to 1.02, and this TS is given by 4 divided by zeta omega n, and at 5 divided by zeta omega n, the system is perfectly at steady state, output is equal to 1. So is it understood that this is the response, and this response actually steadies at 1 volt at the output. So input given is 1 volt, output response is equal to 1 volt. That means steady state error is equal to 0. all these times you have to study, so all those formulas will be given to you. So first time is rise time, so first time for me is delay time. So when you are writing these notes, first time you have to write delay time, time taken for the waveform to reach to the 50% of 1, that is called as delay time. Then rise time 100% of 1, then peak time, when it is going to the peak it is called as peak time. Then percentage mp, here it is shown as mp. So if this peak is 1.4 and this input is 1, then mp is called as zero point 0.4, that is 1.4 minus 1. If I ask you percentage mp, in that case you have to do 1.4 minus 1 by 1 into 100. That is y at tp, y at tp is 1.4, y at infinity, y at infinity means steady state amplitude. Steady state amplitude is 1 because the waveform or the system is generating capacitor voltage same as the input voltage. Okay, so steady state amplitude or steady state output of the system is equal to 1, that is equal to y infinity. So y tp is at peak time, y infinity is a steady state, that is same as the input 1, and denominator again 1 multiplied by 100. So if I say that at y tp amplitude is 1.4, और ये याद रखना, for any system we should not design the system RLC value in such a way that the peak is going above 40%, वो बहुत ज़्यादा deviation है, it should not happen. So maximum we should try to keep the percentage MP, because more is the amplitude, system is becoming more unstable. So though the system is having a underdamped response, underdamped means zeta is between 0 and 1, but we should not keep the peak value more. Okay, so we have to design the RLC value in such a way that the percentage MP or MP, it is maximum 1.3 or something for input of 1. Yeah, that you have to see. So I think this page, all the things I have explained, what is TR, what is TD. TD is not here, but it is 50%. You can come here, understood. What is TP, what is MP, and what is TS. So there are two TS. One is called as 5% TS. Formula is 3 by zeta omega n. One is called as 2% TS. Formula is 4 by zeta omega n. And 2% TS is more stable than 5% TS. Next, what we are finding is, you can find here, this is called as tolerance band. Okay, so settling time is plus minus 2%. So if I'm giving input as 1, plus minus 2% means 0.98 to 1.02. So whenever the waveform is entering that, okay, you are finding here, this is the point where they're entering that 2% and staying there within that. Okay, so this point is called as the TS of 2%. So all those things they have explained here. This is 2% settling time, and 5% settling time will be little bigger band. So below 0.95 to up 1.05. 2% settling time is below 0.98 to up 1.02. So both in the positive and negative, the error you have to think. So this is the steady state response. So steady state response for ramp you are finding here. Sorry, step you are finding here. This is the input, and you are finding that after oscillation also, the waveform, output waveform is touching the input and staying with that. So there is no steady state error in that case. What is the steady state error you can find here? What is this input? This input is called as a ramp input. Ramp means slope is 1, and this is actually the output. So at any time you are finding that this is the gap. Okay, this is the gap between input and output. Okay, for second order steady state step response also, I will show you what is the steady state error. So here steady state error is equal to 0 because input and output both are same. Output is touching the input 1, but not every time it happens like that. If capacitor is having some error, you'll be finding that after oscillation, this output will get settled at zero point 0.8 volt, where input is 1 volt. So in that case, difference between input and output 0.2 volt is called as ESS. That is called as steady state error. E stands for error, SS stands for steady state. Here the ramp steady state error is shown. The ramp input is going like this. It is T. Ramp means T or 2T. Second slope is 2T, three slope is 3T. And here is the response. Okay. So whatever is the distance between input and input and output at any time. Okay. So this much is the gap between input and output at any time. This is called as a steady state error, and this error is constant. Now you are finding that the steady state error is increasing. So input is increasing like this, and output is also deviating. So this gap is steady state error, and this is increasing with respect to time. You are finding. Okay, so this is a ESS increasing. Okay, and below you are finding that the steady state error. So this is what I wanted to show you. Okay, what is the final output? Final output has become 0. So after oscillation, you are finding that the waveform has come and settled to 0, whereas input is 1 and output is 0. How much is the steady state error? Input 1 minus steady state amplitude 0. So in this case, huge amount of error is there because the output is settling at amplitude 0, whereas the input is 1. So what is the difference between input and output is called as steady state error. 1 minus 0 is equal to 1. Okay, so this is one slide that I wanted to show you. Many small cases are there. Now I will go to exactly my handwritten notes, and whatever is time remaining, some 10-12 minutes, there we will discuss. So it's a 15-page note, and this is a very good note that I have written. So I will launch it and I will show. Meanwhile, if there is any question, you please let me know. Vinay, any question? Meanwhile,
No, sir.
Rutik.
No, sir.
Okay. So is this circuit familiar to you? First order or second order?
First order, sir.
This is a first order circuit because there is only one capacitor. How to find the transfer function? So ये सब हम देंगे. You have to prepare this. So this circuit is having a transfer function of 1 divided by 1 plus RCS, and we are finding the system time constant. So time constant is given by R into C, and this is how the step response of the system is going on. Okay, so in this case, first diagram also, the output is reaching to the input, and in the second case also the output is reaching to the input. But in this case, first case, we are finding that the output is slow. Okay, that because the time constant is large. In the second case, we are finding that the time constant is small because the output is rising fast and it is catching the output very fast. So lower is the value of tau. Tau means this is the distance tau. How to calculate it to 0.63 kya hai? That comes from the formula. I will tell you. Okay, so I'm not going for any discussion in time constant for first order system. We will do it during the MATLAB day. Okay, so this is two waveforms. Both are step responses because input is unit step. You can see, but first case here the tau is large, so waveform takes quite a lot of time to reach to the output. That means in the first diagram the system is slow. But in the second case, you are finding that RC value, you can say this is, you can say RC first order system. So how the capacitor is getting charged, that actually I'm showing it to you. So in this case, the tau value is less. That means system is very fast. Let us go for the second order system. Okay, so now this proof is there. I think you can do this proof on your own because we have done the same kind of proof when we have done MBK system or RLC system. Okay, so the full page is visible to you, right? The width wise full you can see. Okay, length wise I cannot see. So what you have to see is V in. So whenever you are writing V in, the same thing is there, R into IT plus L into DIT dt plus 1 by CIT, and you take it into Laplace domain, you find R plus LS plus 1 by CS. And what is the output? Output is nothing but output across capacitor, that is 1 by CS into IS. Now you do output by input. What you find is it is 1 by CS divided by R plus LS plus 1 by CS. So this note will be given to you and you please prepare. And with some kind of multiplication and all these things, we just rearrange it and we find that numerator is 1 by LC. Okay, this is omega n square, because now the most important part, so you can take a screenshot of this part. Okay, this is the most important part of the system. So what is the transfer function? Transfer function is 1 by LC. I told you that omega n is equal to 1 by root LC. So if omega n is 1 by root LC means 1 by LC is omega n square. So this top part is 1 omega n square. And in the denominator also you are finding first term is s square plus r by L. So r by L is actually 2 into zeta into omega n. What is the formula of omega n? So omega n is 1 by root LC. Fn, f is frequency, f is given in hertz. So how to go from omega to f? Just divide omega by 2 pi. You are getting the f. So what is omega n called? Omega n is called as a natural frequency undamped. Okay, undamped means when zeta is equal to 0. That means r is equal to 0. So there is no r formula in omega n. That one thing you can see, that while you are finding omega n, there is no resistance component in that. Omega n is given only by the inductor and capacitor. An inductor and capacitor actually forms the tank circuit. Tank circuit is used for oscillation or generating some kind of sinusoidal waveform. So in your analogs and all these things, you might have generated oscillator. So oscillator is nothing but a sinusoidal waveform generator, which is nothing but a circuit like this. So I give step input, but I get a oscillation output. And how much frequency you want to generate? So LC is in your hand. You can control the LC to get Fn. I want to generate 1 kilohertz. That means Fn is equal to 1 kilohertz. L value, suppose 1 Henry you can keep, and accordingly you can calculate the value of C, and you can plug it in the circuit and it will generate 1 kilohertz. And what is the formula for damping zeta? Damping actually is related to the stability of the waveform, the opposite the gain. Okay, so more is the value of zeta, less will be the value of gain. Okay, and more is the value of zeta, more will be the value of R. So more is the value of resistance in the circuit, you will be finding zeta is more, stability of the circuit is more. So now you can find here there are four cases. First case is zeta in between 0 to 1, that is called as underdamped. So here I have written zeta less than 1, and left side also I should write in between 0 to 1. So third case actually we have to take as second. First case is zeta is equal to 0. Now it is called as no damping. So there is no damping, means nobody is restricting the operation of the RLC circuit. So it will be oscillating. Okay, so that is called as zeta is equal to 0, undamped or no damped. Second case is zeta in between 0 and 1. This is a third case, it's called the underdamped system. Third case, zeta you are increasing. So zeta is equal to 1. It is called as a, so whatever is written in the fourth, zeta is equal to 1. It is called as a critical damping case. So you keep R is equal to 2, L is equal to 1, C is equal to 1. In that case, you will be finding that zeta value becomes 1. So R is equal to 2, C is equal to 1, L is equal to 1. You will be finding that zeta value is equal to 1. Okay, that is called as critical damping. Very important thing, because when we will go into the fourth chapter, root locus, at that time this critical damping thing will come. And it's having very big significance. I will explain you there. So it is written at zeta is equal to 0. That means when there is no resistance in the circuit, the natural frequency omega n is 1 by root LC. The circuit will oscillate output. With damping ratio increased, okay, the system oscillates with frequency omega d. So initially there is no R, omega n. Now little bit of R I am inserting in the system. So first omega 0, R 0, zeta 0, undamped. Little bit of zeta, it becomes underdamped. More is the zeta, it becomes critically damped, and R value very high. Okay, or zeta value very high. It is called as overdamped. Overdamped system is slowest, and undamped system is fastest. That you have to remember. Okay, so undamped means zeta is equal to 0. It is the fastest output, and zeta very big, 5, 10, 15. This is very slow output, so response of the output will become very slow. Okay, so whenever there is a damping, that means R value is present, at that time the circuit oscillates with a frequency. That frequency is called as omega d. Omega d stands for damped natural frequency, and omega n stands for natural frequency. And obviously omega n is greater than omega d. How much is omega d? Omega d is omega n root under of 1 minus zeta square. So omega d is called as a damping frequency or damped natural frequency, and its value is less than omega n. Now, depending on the pole position, what are the things? So as we don't know pole position and all these things, let it be. So this is another diagram you have to remember. Don't see the left side, don't see the pole zero position. फिर से I will come again to this diagram in the fourth chapter. When we do pole zero position, again we will come. Just see the responses. So the fourth response, whichever is given in the fourth quadrant, this you should do first. Okay, this is the undamped response. Undamped means it is equal to 0. This is a natural frequency, but it is above 0 axis. This is a sinusoidal frequency not cut by 0 axis. This is actually a clamped. You have done the clipping clamping circuit. This is actually a clamped sinusoid. That means the whole sinusoid is going up, and this is looking more like a cosine waveform, inverted cosine waveform. Okay, but it can be represented as a sine waveform. So this is the response of a undamped. When zeta is equal to 0, R is equal to 0, this is the response of an undamped case. First case, this is the underdamped case. I told you that R is equal to 2, R is equal to 1, C is equal to L is equal to 1. That means zeta is equal to 0.5. In that case, you will be finding that there will be oscillation of omega d. Omega d is equal to omega n root under of 1 minus zeta square. And that oscillation will die down, and eventually the output will become steady state, and the output will touch the input, and output will stabilize at 1. So it is starting from 0, and then it is undulating, okay, up down, and then at a certain point, TS 2%, 5%, whatever, it will stabilize at peak amplitude 1. So initial part, whenever undulations are there, this is called as transient. Whenever it is getting stable at 1, this is called as a steady state. So this fourth waveform, that is the undamped waveform, this you should explain first. I will ask you the question, so you can write down the question that What are the time specification and amplitude specification of second order RLC system? Okay, you have to mention all this: rise time, peak time, delay time, settling time, percentage overshoot with their equation. That equation also I will show you below. That is the first question. And second question is, for every damping coefficient, how is the output of the second order RLC circuit? So these two questions we are doing today. First question is, what are the different time specifications? With equation, with diagram, you have to show that, and you have to draw that second order diagram, and you have to mention what is rise time, delay time, peak overshoot, and all. And second case is, you have to tell me what are the different outputs. Okay, that is underdamped, undamped, and this top one is called as a critical damp. Here also you are finding that output is reaching to the input, it is touching, but it is rising very high. So critical time is zeta is equal to 1. That means R is equal to 2, C is equal to 1, L is equal to 1. Okay, in this case, it is rising very fast, but it is not rising above the input. You can find here, it is not rising above the input. So this critically damped response is almost close to step input. Okay, so if zeta is equal to 1, at the time output and input, they almost look like same. Okay. Now still further you are increasing the value of R, you will be finding that output is rising very slowly. Okay, and after quite a long time, the output will touch the input. And here you can find the difference between step input and output. And here you are finding this is the steady state error kind of thing. Whereas in critical damping, you found that output is touching the input exactly at a certain point. Okay, so there is no gap between the input and output, steady state error is zero. In the underdamped case also, you are finding output is touching the input, steady state error is zero. But in case of overdamped, when R value is very high, at that time you will be finding that the output is not rising very high, and output is settled a lot below than the input. So this distance between input and output is called as the steady state error. So now last thing I will just show you, I will not do this, and this is the kind of a diagram that you have to draw in the exam. Exactly this diagram you do, and this is delay time, this is the equation, then there is rise time equation, then there is peak time equation, and then there is a settling time equation, percentage peak overshoot, all these equations are there, and I have solved many problems. Okay, so many problems, very small problem, but this problem are asked for 10 marks. So all these things we will be doing tomorrow. So we will attack the second order underdamped response in a bigger manner. We will see little bit of proof, more than proof. We will see all the time and amplitude specifications, and from there how to do the numerical. And for any given transfer function of the second order system, how to calculate all this: rise time, delay time, peak overshoot, all those things we'll be calculating. And tomorrow I want you to sit with a calci, and all the calculations in this case will be in radian. Okay, that is one thing very important. So Rutik and Vinay, try to understand how to convert the calci in radian and how to calculate all these things. So radian में एक ही difference रहता है, pi means 3.14 and degree में pi means 180 degree. So this is the only difference, and all the calculations we have to do in radian, and such kind of one numerical will definitely be there in the final exam or something. So you have to prepare this, and all the solved numericals if you do, you will understand everything. So that's all from my side today. So we have started a second order RLC system response, and we have seen mainly four different zeta conditions and four different output at four different zeta condition. And for second order underdamped system, we have seen there are five time and amplitude specifications. All those details are done. So tomorrow we will directly enter the numerical part, and tomorrow we will finish this second order RLC system numerical and response specifications.